In this video, we're going to talk about solving linear homogeneous systems of ODEs. Okay, so we're going to look at the special case where A is an n by n matrix that has constant entries or constant coefficients. So recall that our linear homogeneous system of ODEs, x prime equals a times x, has n linearly independent solutions. So the question now is, how do we find them? How do we find them? How do we actually solve this system of differential equations? Okay, so the other thing that I want to recall before we talk about how to solve this is, remember when we talk about second order ODEs? When we found solutions of the differential equation ay double prime plus by prime plus cy equals 0, we started off by formulating a guess. So we guessed that y equaled e to the rt. We guessed that it had this form, and we ended up deriving the characteristic equation then, or the auxiliary equation from that guess. So I want to do something similar for our system of equations now, even though this is, matrix form. So for my equation, let's guess the following thing. Let's guess y equals, and I'm going to get something of this, same type of form because it worked so well before for our differential equation. So I'm going to guess something of the form e times rt, but on its own this doesn't work because this is not a vector. And the thing that I plug in, for y, and actually in this case maybe it's better if I call it x instead of y, because I need to be plugging in for my vector value function. So let's guess that x, and maybe let's also write x as a function of t. So far I have this form, e to the rt, but x of t is supposed to be a vector value function, so I need some sort of vector here. So let's just multiply this by some vector u. So here r and u are going to be constants. So my variable is the t. So the other part about this is I want to find linearly independent solutions. So it doesn't help me if I pick u to be the 0 vector, because I don't generate a linearly independent solution that way. So we want u to be non-zero to get linearly independent solutions. Alright, so what happens if we take this guess and we plug it in to our differential equation? Okay, so let's go ahead and plug in now. So plugging in, this gives, so on the left hand side I'll have the derivative of x of t. So when I take the derivative of this, the only part that has the variable t in it is the e to the rt part. So I take the derivative of that, which will be r times e to the rt. And then the u is a constant, so that'll stay there. So that's my x prime. So this is x prime right here. And on the other side, I'll have a times the vector x, which is e to the rt times u. So this is a times x. But notice that what we have is a times this vector, e to the rt times u, is equal to this constant r times that same vector. So I'm highlighting that vector in yellow here. So this means this is true if and only if e to the rt times u is an eigenvector of A with corresponding eigenvalue. The eigenvalue is that number in front. It's the r. So eigenvalue is r. Okay, and there's one important simplification that we can make to this. So if we have something like this that's an eigenvector, notice that the e to the rt, this is not 0. So we can scale our eigenvector. So if we scale this, we can divide by e to the rt and get that u is an eigenvector of A. Okay, so what we've just seen is making a guess that has this form, e to the rt times u, it's going to work as long as u is an eigenvector of A and r is its corresponding eigenvalue. Okay, so we are ready to state the key theorem. So this theorem says if, okay, a little too far ahead. Okay, so if A is n by n and has eigenvalues r1 up to rn that correspond to linearly independent eigenvectors, u1 up to un. So it's really important that they correspond to linearly independent eigenvectors. But the eigenvalues themselves are not necessarily distinct. So not necessarily distinct. Then we can form a fundamental solution set by using the idea from above. So we take e to the, so it's the eigenvalue times t, and then multiplied by its corresponding eigenvector, which I'll call u1, and then comma dot 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 up until the last one, so e to the eigenvalue rn times t, and then times its eigenvector un. So this is a fundamental solution set. And what that means is all of these vector functions in here are solutions, and moreover, there are n linearly independent solutions. So in other words, this forms a basis of solutions for my solution set to my homogeneous system of equations. Okay, so now that we have that fundamental solution set, we can write down our general solution. So the general solution would have the following form. I just take all linear combinations of these linearly independent solutions. So that's why we get x of t equals c1 times that first function, e to the r1t times u1, plus dot dot dot, plus cn times this last vector value function, e to the rn of t, e to the rn times t, and then times the vector un. So in this formula, c1 up to cn are real. The ri's are eigenvalues, and the ui's are eigenvectors. So I'm going to say these are eigenvectors of A, the ri are eigenvalues of A. Okay, so next I want to give a proof for why these functions, all of these functions here, are linearly independent. Alright, so how do we prove this? Well, so we know that e to the r1t times u1, comma dot dot dot, up to e to the rnt un. These are all solutions. These are all solutions of our equation. X prime equals ax. All right. And actually, no, I don't need a comma here. And that the set of solutions of that system of differential equations, so x prime equals ax, has what dimension? It has dimension n. So the set of solutions of this system of differential equations has dimension n. So far I haven't really said anything new. I've just said what the theorem was telling me. So I know that these are all solutions of that differential equation based off the derivation that we did. And we know that the set of solutions of this system of differential equations is supposed to be n-dimensional. So what it remains to show then? It remains to show that the set of solutions, so that has all of these solutions in it, so the set e to the r1t times u1, comma dot dot dot, up to e to the rnt un, that this is linearly independent. Because if something has dimension n, and if I can find n linearly independent vectors in there, they will form a basis for the set of solutions. And that's what will make them that will make them a fundamental solution set. Okay, so how do we show a bunch of solutions to a system of ODEs is linearly independent? Well, we can use the Wronskian, which we talked about in a previous video. So let's form the Wronskian of these solutions. So the first one is e to the r1, t u1, and then comma up until the last one, e to the rn, t un, bracket, and then parentheses t, because it's a function of t. So the Wronskian is the determinant, so that's why I'm going to write a vertical line to indicate determinant, and it's the first vector valued function, e to the r1t, u1, up until the last one, e to the rn t, un. So we're going to take this determinant. So because these functions, e to the r1t, u1, up to e to the rn t, un, because we know that they're solutions of our system of ODEs, that means this Wronskian is either always going to be 0 or it's never 0. So let's plug in a specific value for t to figure out what it's going to be. So let's plug in maybe the simplest thing that we can. Let's plug in t equals 0. If we plug in t equals 0, then we get the Wronskian of our functions, which I'll just write a squiggly line so I don't have to write it all out. So the Wronskian of our functions, but now evaluated at 0. So what do we get if we plug 0 in for the t for all of these? So the e to the power will be e to the 0, and e to the 0 is 1. So what we will be left with is just the vectors u1, up until un, and with their determinant. But the given portion of this theorem said that we were assuming that the vectors, eigenvectors u1 up to un, were linearly independent. So that means this determinant is not equal to 0. Not equal to 0, since u1 up to un are linearly independent. We were assuming that we were in the situation where our n eigenvectors were linearly independent. So because, just to recap again, because these functions were solutions to our ODE, that means the Wronskian is either never 0 or it's always 0. And now we've plugged in a specific value for t and found that the Wronskian is not 0 for this specific value of t. But that means that the Wronskian is never going to be 0. So the Wronskian is never 0. And because the Wronskian is never 0, that means our set of solutions, e to the r1t u1, up to e to the rn t un, this is linearly independent. And that's what we needed to show it's a basis. So let me just say, so we are done. We wanted to show that these n vectors were linearly independent because that shows it's a basis, and now we've done that. Alright, so let's do a quick example, and I'll end the video with this. So let's find a general solution now to a system of ODEs. So let's find, okay, so I want to do it in the case where my matrix A is -2, 3, 0, 4. So to do this, we need to find the eigenvalues and the eigenvectors. So to save time, and because we've found eigenvalues and eigenvectors a bunch when we were in chapter 5 in linear algebra, I've gone ahead and worked those out, but you should check this. So check my math on this. So I got my eigenvalues were -2 and 4. Those we can actually see by looking at this, because this is an upper triangular matrix, so the eigenvalues are along the diagonal. But check that the eigenvectors that go with them are 1, 0 for -2, and the other eigenvector for 4 is 1, 2. Okay, so now that I have those, I can formulate our general solution. Our general solution, our vector valued function, xt, is going to be c1 times e to the first eigenvalue, -2, t, times its eigenvector, 1, 0, and then plus C2 times e to the next eigenvalue, 4t, and then times its eigenvector, 1, 2. And that's it. That's our general solution. That is the general solution to this differential equation right here. So if we can find the eigenvalues and the eigenvectors of this matrix, as long as there are n linearly independent eigenvectors, and here there were, I can write down my general solution in this form. So a natural question is, it's not always possible in a matrix to find n linearly independent eigenvectors. So the question is, what do we do if we can't? So what are the solutions to our system of differential equations if instead of is, if A does not have n linearly independent eigenvectors? So this we are not really going to talk about, but I'll briefly just answer the question. It turns out we will, to do this, you would need to use what are called generalized eigenvectors. Okay, so that is the topic of section 9.8. So we won't really be talking about this, but if we were interested in answering this, we would use this thing called the generalized eigenvector.